Today we're going to look at adding things that have rational exponents. So in my little drawing up here, I've tried to add 2 flowers plus 3 flowers plus 4 stars minus 3 stars as a way for you to recognize that we're going to add like things together. So if I was going to simplify this little expression I have here, I would say I had, and these are in red, so that's also helpful, 5 flowers, and then plus a star. That's a terrible star. There we go, better star. Because 4 minus 3 stars is 1 star. Does that make sense? Like from a purely, if you were in elementary school and you would add like things together, these would be symbols for that. Okay, so what we're going to do first is we want to define like terms again. We did define like terms in Algebra 1. I said define terms. Define like terms. So like terms means that obviously x and y are not like terms. They don't have the same variable. So like terms have to have the same base and the same exponent in order to add or subtract them. You have to have the same base if you're going to multiply, but you can have different exponents if you're multiplying. We did those already. But if you're going to add things, they have to be exactly alike. And I'm going to show you 2 ways to think about this. One of them might work better for you than the other, depending on just how you think about things. You could have done this problem by like factoring out the shape. If I said I had flour and I factored out of the red, I would have 2 plus 3 left over. So they both have a flower. If I factor it out, I'd have 2 plus 3. That makes 5 flowers, 5 flowers. Over here, if we factor out the star, we'd have plus star, and we'd factor that star out, we'd have a 4, and this star we'd have minus 3, and 4 minus 3 is 1 stars. So factoring is one way you're going to work it. Another way is to just look at the rule, same base and same exponent, so that we can add and subtract things. So let's see some examples so you can see what math I mean. So for example, first one up, I've got, we'll say something even simpler than what they have. 2 square root of w plus a 4th the square root of w. So as you write that down, what I want you to recognize is that the 2 and the 1/4, they're the coefficients. And coefficients mean how many you have of something. It's the number in the front. We've always sort of defined it as the number in the front, but it really means the quantity of whatever follows it. So in this case, what we have following it is the same exact thing. The base is w, and its power is square root, or you could say 1/2. This one's got a base of w and a square root of 1/2. And to add these together, I'd probably want to change this into like, what, 8/4? That would be okay, right? 8/4 is equal to 2. And then I could say, well, how many square root of w's do you have? So this is the way I explain it without factoring. And some people like this method. I think about if I can take whatever follows the coefficient and put it in a box. Like I've boxed it all up. And if the boxes look exactly the same inside, then I can add the coefficients together. And I would say I have 8/4 plus 1/4 is 9/4. And then I keep whatever's in the box, the square root of w. If I try to box up what's after that coefficient and they're not exactly the same, I can't add them together. They're not alike. Okay? The other method for the same problem, I'll keep it as 8/4 and the square root of w and 1/4 square root of w. The other method is to look and see what's common between them, and this is the same as this. So if I take out the square root of w, from this one what's left over is 8/4. From this one, what's left over is a fourth, and then add them together and get 9/4 square root of w, because we normally write the number in the front. You could put it in the back, but that's weird. You get the same answer. To me, the second method is kind of cumbersome if you can recognize that these two guys are the same. So it's kind of just putting a box around it, or mentally putting a box around it, is enough for me to add them up together. But sometimes they get complicated, and you might want to have another way to look at the problem. So let's look at what that might mean. Let's say we have 3xy to the 1/4 minus 8xy to the 1/4. So you're writing that down, 3xy to the 1/4 minus 8xy to the 1/4. And if you use the box method, you would put a box around what? And what else? We need everything. So truly the 1/4 goes with the y. You should notice that. The x has its own exponent. What is that? 1. So this is x to the first, y to the 1/4. This is x to the first, y to the 1/4. They have the same thing. And so if we put this in a box just to have a visual of it, and we compare the boxes, everything in the box is the same. And the numbers in the front represent like how many of those crates we have. We have 3 crates. Subtract 8 of the same kind of crate. How many crates do we have? We have -5 crates, and we just rewrite the stuff in the box. So these numbers, count them up, and we just put everything in the box and see if it's the same. And if they are, we can add up those, we can count the number of boxes. So -5, keep the stuff in the box. But it is important, and I just want to say it one more time because it's that important. This 1/4 doesn't go with the x because it's not in parentheses. X has its own exponent, 8 has its own exponent, 3 has its own exponent. So you do have to know all of those little things as you go. Now this one's a touch more complicated. Our C example says 12 times the cube root of 2z to the 5th minus z on the outside, the cube root of 54z squared. So write that down carefully because it's got a lot of stuff happening. 12 cube root of 2z to the 5th minus z cube root of 54z squared. Right now, obviously, they're not the same, right? If you put it in a box, they wouldn't be the same. But the second one, even the first one. The first one, is there anything we can take out of the radical? We could make the radical a fraction. I think that might make this one a little bit more complicated that way, because I've got both things in here. So instead, consider that there's 5 of these z's. Do we have enough z's to take out any? We could take out 1 and have how many left over? If we take out, so we'd have z, 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 right? So we take out 3 of them because that says 3. Okay, so I'm going to have 12, and I'm going to take out a z, and I've got 2 left over. Cool. Just kidding. So we don't have enough 2's to take out. We took out a z. We have 2 left over, so I'm going to write the cube root of 2 stays in there and z squared. This still doesn't look like my second one yet, but it's as simple as it can get. What's the coefficient for this green term? 12. It's actually 12. 12 counts up how many I have, and even the z goes in the box. Okay, so that's going to be what I box up, all that stuff, and I'm going to see if I can get the same thing out of the other one. I've got a z on the outside. Can I take out any of these? No. So they're going to stay. 54 though, how about, okay, so I should rewrite this. This is going to be z, the cube root of, tell me 54. How can I rewrite it? Nine times 6. So 3 and 3 and 3 and 2. So that's 3 and 3 and 3 and 2. That's all multiplication. That's not 3,332. Z squared. So I'll put little dots in there. Can I take out anything now? So we take out a 3. Now I have a 3 on the outside and a z. I have a 2 and a z squared left. Cube root of 2z squared left. In the second term, 3 or negative 3 is how many I have. Everything that follows that has to match the first one. So I have z to the first power and the cube root, and in the cube root is a 2 and a z squared. Are they the same now? So do you see the box, how that's kind of helpful? It puts everything after the coefficient together and everything must match. And since they match, I can say I've got 12 boxes and somebody's going to take away 3 boxes. How many boxes do I have? 9 boxes. And then I just repeat what's in the box. Z cube root of 2z squared. So these are like terms because every single thing inside the box is the same. Base, exponent, and then base, even radical. So that is represented as an exponent. So this would be the more complicated version where you might have to simplify your stuff and then see that they have the same terms. How we doing? Okay? So I think that this method's easier than factoring it out. I don't really like how I'm factoring it out. Okay, so that's really all there is in this lesson. You could have the method where we have the radical here or written as an exponent. And as long as everything matches, then you're cool. You can add them up. So you've got a few minutes, or you can eat lunch and then go to Powder Puff. And then be early. So whatever. But here's your homework. This is due Monday, not tomorrow. This is the last of 6.2. So it's 32 through 40. That's about 8 problems, and then 60 through 65. So just write them carefully. This is page 424. So just write them carefully because there is a lot, small details that has to be right for the problem to be right. But it's totally manageable if you know the rules set up. Yes. Yeah, so, and I've got the video I'm going to post it to, but sure. And I'm still recording. I'm going to pause that. Pause.